Okay, so welcome to the IMA Data Science Seminar. I'm very happy to introduce Yanpeng Shi. So he got his PhD here at the University of Minnesota in mathematics in 2020 with Gilad Lerman. And since then, he's been a postdoc at Princeton. He's working with Amit Singer. And today he's going to talk to us about 3D reconstruction in macro and micro worlds, challenges and solutions.
Thanks, Jeff, for the introduction, and thanks for inviting me to give a talk here. So today I will talk about the 3D reconstruction into different regimes. So specifically, I'll talk about two problems. One is structure for motion. The other is a cryo-electron microscopy imaging, namely cryo-EM. For these two problems, these two problems are pretty broad areas, and in particular, I will focus on two subproblems, respectively, the group synchronization and the covariance estimation problem in these two regimes. Okay, let's start with the first part, the structure for motion. So this is a Notre Dame Cathedral that was born, partially born a couple maybe in 2019, and they claim that they have to fix it. They cannot fix it until like 2024, but if they want to recover it, they need to somehow know the 3D model of it, right? So how can I do this? So one solution is the structure for motion. Okay, so what you do is that you take a bunch of images of this building, taken from cameras from different directions and locations, and you want to recover this 3D structure of this building from these 2D images automatically. Okay. So this is what you got from typically what you got from a structure for motion pipeline, and later you will do something like dense surface reconstruction using some interpolation. But now the first goal is to get this sparse point cloud. Okay, but to estimate this initial 3D structure, okay, you need to know the camera locations and orientations. Okay, so these are, if I zoom in, these are the set of cameras whose orientations are kind of estimated and shown here. These camera orientations are critical to reconstruct the 3D structure, because you need to know exactly what are the camera parameters, like their orientation, so that you can starting from the pixel value and trace back and intersection in the 3D space, so that you can estimate where this pixel value comes from in the 3D space. Okay. So, but the question is, okay, how do you estimate camera orientations? So, for each pair of two images, usually what you start is that, okay, you can figure out the so-called key point match between the two images. Like the corner in this window corresponds to the corner of the window in the other image. This kind of correspondences, if you can find them accurately, for example, these two images are taken from two cameramen, okay, from two different directions, and you somehow want to use 3D multi-view geometry to starting from this key point match to find the relative camera orientation. There's some math involved here, but I won't go into details. It's kind of unrelated to my talk today. But assume that now, okay, you can get for each pair of image, for some pairs of images, you know the relative orientations. Okay, from this key point match. So how do you estimate the global, absolute camera orientations from these relative ones? So this is a general mathematical problem. Okay, so assume that, okay, you have a graph, and each node is a camera, and for some pairs of the cameras, you know the camera orientations, relative camera orientations, which is represented as edges in this graph. Okay, so you have the N is a set of nodes and E is a set of edges. So in this problem, okay, each camera I is assigned the unknown ground truth orientation, GI star. Here I use star to emphasize it's a ground truth, but you don't know what it is. It's some underlying parameter you want to estimate. Okay. And each edge is given a positive noisy and corrupted relative orientation. It's positive noisy and corrupted because there's some errors in the k-point match. So this error accumulated along this pipeline. So you got some error in your relative camera orientations. So the clean orientation Gij star is defined as Gi star Gj star inverse. So this problem asks to recover the absolute camera orientations from this possibly noisy and corrupted relative orientations up to a global location. Because if you have a Gi star as a solution, then any Gi star times the same G0 should also be the solution of the problem. Okay, so there is a global rotation ambiguity. Now let's consider, like, generalize this problem to a broader class of a mass object. So now we know that camera orientations are rotation group which belongs to SO3, right? So now we can generalize to arbitrary group G. So in this new setting, the Gi star will represent the absolute group element, and Gij will represent the relative orientation. Oh, sorry, the group ratio in this new setting, in this much more general setting. And again, similarly, the clean group ratio is Gi star, Jj star equals to Gi star, Gj star inverse, and the definition doesn't really change. Okay, we can define in the exact same way. What's significant about this problem is that it has many different applications, even though in very different regimes that seems far away from each other, but they have a very similar mathematical structure. So for example, if G is SO3, you know, it's a camera orientation estimation that I just introduced. Okay, but if it's U1, it becomes, it has applications in ranking and phase retrieval. Okay. If it's a permutation group, it corresponds to the multi-image matching. Okay, because each pair of images, the k-point match can be encoded as a permutation matrix. And if it's Z2, then it has applications in so-called correlation clustering, and has applications in community detection like stochastic block models and so on. Okay. Since it has a very general applications, the natural question is that, okay, can we solve GS in this general setting in a unified framework? How to solve this problem? All right, so in the previous work, okay, there was a standard solution that at least works for any subgroups of OD, the orthogonal group, with dimension capital D. What they do is that, okay, now in this, if we make this assumption, then Gi star and also the relative orientation, relative group elements both can be represented as a D by D orthogonal matrices. So what you can do is that, okay, you can stock all the absolute group elements as a very tall matrix. I call it capital G star. And you multiply it by its transpose. If you just do a simple calculation, it should give you a large ND by ND block matrix where each block is just the relative group elements, the group ratios. Okay. So now, what you observe, as I said, is not exact. It's not ground truth. Instead, you have some corruption and noise. So this is only a kind of approximation. So this naturally induced a mathematical question about the low rank approximation of this H matrix. So if you compute the top eigenvectors, like top D, capital D eigenvectors of this H, and then project each block into this orthogonal group D, then you should be able to recover approximately this G star, hopefully. Okay, but unfortunately, this naive spectral method is very sensitive to outliers. I mean, only for G groups, Lie groups. If it's a discrete group, it's not a story. Okay. This is an example. Like if you have even there is this horizontal axis is a probability of corrupting an H, And there is another probability P for assigning edges that correspond to a sparsity of the graph. But the main message here is that at any point, no matter what's the corruption probability, no matter what's the connection probability, the spectral method always give you a non-zero error.
When you say that edge is corrupt, what is that?
So it means so you have Erdo-Schrödinger graph, and for each edge, it's corrupted with probability Q. If it's connected, then it has a further probability of being corrupted. If it's corrupted, then you randomly assign a new group elements that is randomly distributed on this space.
It's completely random.
It's completely random. It has
it's not close to the true one.
Yeah, it has nothing nothing related to the ground truth one. Yes. So it's called corruption. If I say it's noise, that means you have really additive noise. But if I say corruption, it means I remove the original information. Okay. P is that for two nodes that you have a probability P of connecting the nodes and have an edge. But Q is that if you have an edge, what's the probability of being corrupted? Okay. Another challenge of this type of problem is that it's typically computationally intractable for large N and D. So assuming this problem, so the reconstruction problem, usually if you consider the case of G is a permutation group, which has a application of multi-image matching, the scale of N and D is like 1,000 and 10,000. So this matrix H, it takes around 800 gigabytes memory. So it's definitely computational intractable, even just consider space complexity, not even mention the time complexity. Okay. So in order to achieve robustness, so usually what people previously do is that you run some least square solution method, like a spectral method, and you got a rough solution. And then you look at residual, and this residual tells you how good these edges are, how good these bad edges are. And you look at this residual and assign a weighted graph, assign weights to the graph, and you run a weighted spectral or weighted least squares again, and update the weights and update least square solutions iteratively. Okay, but you, as I said, sometimes the spectral methods or least squares methods are so computationally expensive. In some cases, you don't really want to do it. So the question is there a way that efficiently and accurately estimate this edge corruption level in order to achieve robustness, where you can also completely avoid estimating the group elements? So here, the corruption level, I define this as Sij star equals to some distance between Gij and its ground truth. Okay, so I'm not just classifying edges, I'm also estimating the corruption level exactly. Okay, I want to know what's the degree of corruption. Okay. So as I said, the original problem can have very high dimension because the capital D can be very large. So the first thing I want to do maybe is that to reduce the capital D into a number. So what you can do is actually you can look at this cycle consistent constant. So this is a very natural idea where if you have a ground truth group ratios, if you multiply them along cycle, it should give you identity. Any question here about these properties?
So what is the risk?
It can be quite arbitrary as long as it satisfies triangle inequality and it's bi-invariant. Oh, sorry, I'll talk about this later. I define this later, but it can be quite general.
You can give an example.
So for example, in SO3, you can pick a geodesic distance, or you can even pick the difference between the two group elements and then take the Frobenius norm. Okay, so let's first assume a corruption model where we need to clearly define our goal and our method. So assume you have a graph, and for some of edges it's clean, and I call I call them EG. Okay, EG I will have later. The EG means good edges. If it's corrupted, I will call this set of edges as EB. I should mention here. But the goal is to estimate the group, the corruption levels for each edge from 3 cycle inconsistencies. Dijk equals to the distance between the group multiplication along group, a cycle and the identity. And if you observe a positive Dijk, it must mean there is an edge that is corrupted in this cycle. But how can you estimate this Sij star from this Dijk in a kind of mathematical way, right? And as I mentioned, I gave a additional condition on this metric, and I make it by invariant. So it's invariant on the right and the left group action. Any question about this problem setup?
So I'm a bit unclear. So if you have the corruption level, does that help you solve the original problem?
Yes, exactly. So the main point is that we want to find some cheap way to compute the corruption levels and then use these corruption levels to solve the group elements in an either accurate way or in a very fast way. So it enables many post processings, and that I will mention later. So motivation of our works, this line of works, relies on a critical lemma. So recall these 2 definitions, and we can actually relate this Dijk and Sij star that we want to estimate by this kind of inequality. It's something similar to a triangle inequality, but not exactly same. Okay, so definitely it says that, okay, if you want to use Dijk as an estimator of Sij star, then this estimation error must be bounded about by the corruption level of the other 2 edges in that cycle. Make sense? Okay, this is the inequality we're looking at. So one direct consequence of this lemma is that if you look at this edge ij, if the other 2 edges I labeled as green, I color as green, are clean or I mean uncorrupted, then this Dijk is an exact estimator of Sij star. So we can even verify this without even using that inequality. So assume that Ik and Jk are good edges. So that by the definition of Dijk, we know we put star on Jk and Ki because they are ground truths, which I assume here, which are labeled as green. And then I can multiply Gij star on both sides of this in this distance function because of bi-invariance property. And then by cycle consistency condition, okay, this Jk star, Gki star, and Jij star cancel each other because they are identity. So got Sij star. So see, we got a kind of condition when this Dijk gives you exact information, and we need to figure out which of these cycles are good cycles, which are bad cycles, in order to estimate it. So there are 2 cases when if one edge is corrupted or the 2 edges are corrupted, this equality is no longer guaranteed. So we make some, before we move on, let me introduce some more assumptions and notation. Okay, so for each fixed edge ij, I call Cij as all the 3 cycles that contains it. And Gij is a so-called good cycle because I define it as the other 2 edges are clean. Okay, for each fixed ij. I make assumption that this Gij is not empty. That means for each edge, there must be a good cycle. And this implies something significant. it implies that this Sij star must be supported on this set. Because if you have a good cycle, if you have many DIJKs like that contains Hij, if there's good cycle, you know that there must be a DIJK that equal to Sij. And you need to find it out. A good benefit from it is that you kind of reduce the search space of your Sij star. From the continuous space of R, you restrict that to a discrete space. Now you can, based on the discrete space, you can define a distribution. And you can represent this efficiently because it can be encoded in a 1D vector. Okay, for each edge Ij. For each edge Ij, you sample some 3 cycles that contains it. And for each cycle, you can give a cycle a kind of probability that whether it's a good cycle or bad cycle. And this probability mass will form a histogram, or actually you can call it a distribution. And you can use this distribution as an approximation of the distribution of Sij star. So ideally, you hope that this distribution will focus on this cycle, these good cycles. Because you know that, okay, for example, Dij K2 and Dij K4 are good cycles, so they have exact, they equal to ground truth. So you hope that the probability mass will focus on these 2 cycles, and all the other cycles will have a kind of probability 0. Okay, how this will help with, solve the problem? A very intuitive idea is that it assumes that you have your current estimate of the distribution of Sij is like this. So if you know the distribution, how do you estimate its value? If you there are several ways. Okay, so for example, we can use expectation of this distribution as an estimate of Sij star, right? And if we know this a better estimate of Sij star, we can in turn in return define calculate a better cycle probability to form you a better distribution. And the better distribution will give you better Sij, and better Sij gives better distribution. You can iterate back and forth. Right, so for example, from a better Sij, you can look at, okay, you have better sense like which edge are good, which edge are bad. So you can find, exactly locate the cycles that have clean edges. Okay, any question here? So this method is called cycle edge message passing because you kind of iterate between the edge estimates and the cycle estimates. We actually can show some nice convergence result, not just empirically but also in theory. But I won't go into details about it. But instead, I will focus on some limitation of this problem. So for example, as you can see that this update rule about the Pijk by the exponential function with some parameter beta t, it's actually quite a little bit heuristic. So the question is that, can we mathematically explain this more clearly? Is there a interpretation, or does this message passing procedure really minimize some objective function? We don't have an answer yet, but motivated by this question, we may ask, okay, maybe we can estimate this Sij and this Pij together in an optimization framework. Okay, so this is the goal of of my recent work with Gilada, another student. So this relies on the following proposition that relates the Pij and Sij star. Any question on this lemma? on this proposition. So let me. So what we have is that okay, we can for each edge, this Pij star it encodes its probability distribution information, and the Dij encodes the cycle inconsistency information. And we can show that the inner product of Pij star and Dij is exactly the Sij star. And I will explain it. And also there is a orthogonality condition that this Pij star is orthogonal to the Vij star that contains information about corruption levels on the other two edges in that cycle. Okay, so first for the first constraint, it's pretty simple because Pij star means okay, you have a probability mass that concentrates on good cycles, and if you do the inner product with this Dij case, we know that by the proposition that good cycles give the exact estimate, you automatically get Sij star. Okay. On the other hand, you can prove that this you can prove this orthogonality condition that if you look at each element of this inner product, so we know that by the definition of Pij star, it's all the probability mass, because it's ground truth. We use star to emphasize the ground truth. Okay, so each of these elements are concentrated on good cycles. So if I add the indicator function like k belongs to good cycle, it doesn't change anything, right? Because we know a probability mass concentrates on good cycles. But what does it mean? What does it mean? It means if it's a good cycle, then it must have the following implies the following condition: Sik star plus Sj star must be 0, and consequently, you get 0. Okay, so now we know. Okay, so we have the nice constraints, the two constraints between the Pij star, the distribution of corruption level for each edge, and the Sij star, the corruption level itself. Okay, and these two have actually a kind of a relationship. So can we, based on these two constraints, to formulate a optimization problem? And yes, we have the following quadratic programming problem. For example, the object function corresponds to the orthogonality constraint. And we also put this Sij equal to Pij transpose Dij in the constraint. And we make sure that Pij is a probability, is in a probability simplex, so that the sum of this element is 1, and all the elements are non-zero. Any question about this quadratic programming object function? So it's indeed a quadratic programming problem, because if you just plug in this Sij in the constraint to the object function, you can just simply minimize Pij, right? And you will see you have some cross term here, which gives you a quadratic problem. A kind of interpretation of this object function is that it minimizes, all object function minimizes its it's actually upper bound, approximate upper bound of this accumulative error of corruption levels. So of course, in the first term, you really don't know what is Sij star. So you don't have access to you don't have access to it. But what you can do is that, okay, I can replace this Sij by my definition in my constraint, right? It's just the inner product between Pij transpose and Dij. Okay, and I can pull out each Pijk, because Pijk sum up to 1. So I can combine the Dij with Sij star together. And then I can put the absolute value inside the sum. And now I use our k-lemma. And this gives us a relaxed version of our, an approximate version of our object function. But we don't know what is Vij star. So we have to switch the Vij star to Vij as a new variable. The next property of this object function is that, okay, if the Gij is non-empty for any age, and the cycle inconsistency Dijk is greater than 0 whenever you have corruption in that cycle, the global minimum of our object function of our formulation exactly recover the ground truth corruption levels. So I don't have to go over the proof details, but the idea is that if you can show that if there is any Pij, the distribution of Sij star that have non-zero mass on bad cycles, you can show that the object function has value greater than 0. And you can further show that the corruption at the global minimum that recovers the corruption levels, the value of the function is 0. Okay, you cannot go below 0, and if you reach 0, you know it's you reach global optimality. And you can start from this theorem and extend its result for compact Lie groups, and you can show that if you have a continuous distribution, you are also able to recover with the ground truth with probability 1. Because if you have continuous distribution on your group ratios, you are pretty sure that with probability 1, any correct cycles will have cycle inconsistency greater than 0. Because you have a continuous distribution, and your corruption model is also your corrupted group ratios also follows a continuous distribution. So based on that corollary, we can show a sample complexity bound, assuming that you have a uniform corruption model that I taught before. So assume that you have a graph where you have some probability of connecting two edges, I mean P, and you also have a probability of corrupting an edge, I call it Q. And under this model, you can actually recover this. You can actually recover the ground truth with as long as n over log n is greater than some constant over p squared times 1 minus q squared. So the information theoretic bound in this problem is of order 1 over p times 1 minus q squared. So we didn't match the optimal bound for p, but we matched for q. Okay, so the reason why we cannot match p because we use 3 cycles. So you cannot handle sparser graphs. But fortunately, for most of the structural function data, even though the graph is not dense, we still have enough 3 cycles for each edge. Any question about the theory? Okay. So for optimization, there could be many different methods, but we only tried a very simple one, a very naive one, just a naive projected gradient descent method. But the one thing special we did is that we always keep that the gradient is within this hyperplane defined by the simplex. So it's something related to the Riemannian gradient descent, but it's not a valid retraction anymore. But we use some ideas there. It seems to work better. Okay, so for real data experiment, we tested our on certain real large scale real phototourism data set. So each data set contains many images from a historical building, and we test and we have approximate ground truth of camera rotations, and so that we can compare. And we can show that our method, because it optimizes the SIJ star in an optimization framework, so it usually gives better results than the original camp. Now we introduce some post-processing from our estimated corruption levels. So as I mentioned, one of the motivation of this work is that we can infer the corruption levels very efficiently, right? Without solving the group elements really. So is there any post-processing we can use to also avoid spectral solution? So one thing we can do is we can use we can start from the corruption levels and build a weighted graph. So the edge weight will be the corruption levels. And we can build, based on this weighted graph, we extract the minimal spanning tree. So the resulting spanning tree will have the lowest average corruption level. So it's the cleanest spanning tree. So that I can propagate along the spanning tree. So for example, I like G1 to be identity. And let G2 equal to G21 times G1. G3 equal G3 to G2, and so on. You may think, okay, the error may accumulate along this spanning tree, but actually, if you have a very clean inlier graph, which surprisingly many structural motion data has, you can actually do a pretty decent job. So, for example, if we use our camp method to estimate corruption levels and then combine with the spanning tree method, it actually achieves a pretty nice rotation estimates, comparing even to the iteratively weighted least squares. It's actually quite comparable. And we can also use, for example, use a camp or desk, use this SIJ star to build the edge weights, to find the edge weights, and then run a weighted least squares, a weighted spectrum method, which may be slower, but it may improve the performance a little bit. We can further use this SIJ star to combine with the iterative weighted least squares. Combine this SIJ star with the residual in each iteration to help this ARS escape the local minimum. And this method so far achieves the best result. And any question about the experiments?
So you mentioned a bunch of applications, possible groups that this would apply. Have you looked at other problems besides structured motion?
Yes. Also, for this one, it's still about structural motion. But next part, I will talk about other problems. But it's not related to group synchronization anymore. But for group synchronization, we mainly work on two problems: orientation estimation and also multi-image matching. And this is for multi-image matching that has some applications in the so-called shape matching and graph matching, and which may have some application beyond the SFM. But yeah, but this is one example that I'm going to talk about. I'm going to talk about comment on the complexity and runtime of this our camp or desk-based method.
I think what you were asking is you only go for SO3, right? What about the permutation group?
Yeah. So what I'm going to talk about is a permutation group. Okay. So if we consider, but a permutation group is also a general subgroup of the of OD, right? So if we assume OD with a very high dimension D, capital D, so it's no longer SO3, it can be SO capital D and also SD or something. And in this case, if we compare sample space complexity and time complexity with spectral method, we actually gain from the sparsity of graph. The P is probability of connecting edge. We're assuming a scenario where you have a Dirichlet graph. Okay. So we can have an option whether we use all the 3 cycles or we for each edge we sample a fixed number of cycles. But in either case, we have some advantage compared to the spectral method. If the graph is quite sparse, sparse means it's far from being complete, but still have many 3 cycles. Yes. You're using for each age, you're sampling maybe 50 cycles or 20 cycles. Yeah, we usually find that's enough. And even if you use all the cycles, we kind of have a pretty good speed up. So this is another application, a multi-image matching, where the capital D can be 1,000, where you have like on a scale like 1 or 2 magnitude order of magnitude speed up comparing to the spectrum method. All right, so this is I'll give a quick summary of the first part, where we propose a kind of fast framework for solving a group estimate the corruption levels without really solving the group elements, and then we propose on the accuracy side that we can have some kind of optimization framework to estimate SIJ star more optimally, which gives some theoretical guarantees and also improved performance in accuracy. So there's some future directions. For example, you can, as Will just mentioned, we can actually extend our work to other applications. For example, in structural other subspace recovery and ranking problem. Okay. And we can also generalize desk to incorporate longer cycles, because now we only use 3 cycles, so that we cannot guarantee match the information theoretical bound in terms of graph sparsity. But if we incorporate longer cycles, we can approach that limit. Okay, so how many time do I have? $10 minutes? Okay, so I will skip some parts of this this application. So in this work, I'm going to talk about electron microscopy images that use that images 3D structure of macromolecules like proteins. And in this work, this work wins 2017 Nobel Prize in chemistry. And this is COVID-19 Omicron spike complexes that is reconstructed this year. Okay, so what is the image process is that you rotate it. Okay, so you have some electron beam that go from above, and you got some noisy images. So ideally, you want to see something like this. It's a clean projection, but unfortunately, you can't see it. What you really observe is you come up with some filter, with Fourier inverse transform of a filter called CTF transfer function, contrast transform CTF. The radial profile is like this. It's highly oscillating, and you got something like this. And you can make it to have a higher contrast, a lower contrast, and add noise. Okay, so this is usually what you finally observe, and sometimes you cannot even see where the molecule is. Okay, so the image forward model is like, okay, you convolve with some filter AI. This AI is a linear operator corresponding to the convolution, and CI is scaling, and epsilon I is a noise. So our task is to estimate the covariance estimation of the clean images Xi from the observation of Yi without knowing anything about the 3D structure. So why we care about this? So for example, if you look at the noisy image and you want to recover what's the original image, this is what our algorithm does. So it's a completely unsupervised method, and it does not require anything about 3D molecule. Okay, so but it's still able to kind of recover. It does a decent job in recovering this clean image. So how can we do this? So there are a bunch of challenges, which I will not which I will not go into details, but I want to emphasize that about the computational challenge. So for example, if we consider a simplified case where we don't have the contrast variations, that's CI, constant, the images are convolved with some filter and add the noise. And you can further rewrite this HI as convolution as a linear matrix or a linear operator. Okay. The common solution is that you can estimate the mean and the covariance of these images by the least squares method. So these are kind of most common method, but still computationally challenging. Why? If you look at the covariance matrix in real images, where L is the dimension of image, can range from 100 to maybe 1000. Okay, so if you have a 500 by 500 image, this covariance matrix will have more than 100,000 by 100,000 dimension. We can take several hundred gigabytes to store. So the time complexity of this covariance matrix estimation can be extremely high, both in real space and Fourier space. I mean, in Fourier space, the convolution can be represented as a diagonal operator, but it can still be slow in Fourier space because the covariance matrix is still quite dense. So some other works that represent the images into Fourier Bessel basis that enables the both block diagonal representation of covariance matrix and the filter, CTF filter, which reduces somehow in some cases the space and time complexity. However, this complexity depends on the number of distinct filters M. So if you have many different filters, like one filter for each image, this complexity will be extremely high. It's not scalable. But unfortunately, many nowadays, the modern cryo-EM fall into this computationally challenging regime, which cannot be handled by any of the previous work. So what we do is that we use a new implementation of the Fourier Bessel basis. So Fourier Bessel basis is eigenfunctions of the Laplace operator on the Dirichlet boundary condition. And the next property of it is that, okay, if you expand the image into the spaces, you can use this, if you convolve this image F with any filter H, it turns out that the resulting image has a Fourier Bessel coefficients at AKQ times some other value, the value in the CTF filter, which means the convolution in real space is a diagonal operator in the Fourier Bessel space. So you can actually represent the CTF as a diagonal matrix. Okay, in real space, it's something dense, but in this spaces, it's diagonal. Okay. What's more important is that it's steerable. That means if you want to rotate the image in the real space, you only need to do the phase modulation in that basis. Turns out that if all the images are augmented by all possible in-plane rotations and reflections, the covariance matrix is block diagonal. This also reduces space complexity. Usually you have hundreds of diagonals, diagonal blocks. And as a result, our method reduces the time complexity and space complexity by large, lower than any previous method. And our method is independent of M. So no longer how many filters you have, no matter how many filters you have, it doesn't matter. So it's the first algorithm that is scalable on modern cryo-EM dataset. So this is a comparison to the previous CWF method on using another Fourier Bessel transform.
That one's same shot.
Yes, exactly. Okay, so we still see some slight increase in time in our red curve, because when you have many filters, you take slightly more memory usage, and you take some more time for array indexing. So it's something technical about the machine, not really about our algorithm. Okay, I'll skip this one, but I just want to show that we have way better eigenimages if we compute it from our coherence matrix. The first one is clean one, the second one is ours, and the third row is the traditional PCA. So it just says that our method does not just have advantage in time. We also have advantage in accuracy, because estimating coherence matrix at this high dimension is a hard problem. This block structure actually reduces the dimension of the coherence matrix. We can solve the coherence matrix block by block, and each one is of much lower dimension. So we cannot overcome the curse of dimensionality, which results in better accuracy.
That's true of any strip basis.
Yeah, that's true for any strip basis. But our main contribution is also that we also can expand CTF as a diagonal operator, which was not done in previous work. This one?
Which part of the
block diagonal is like space complexity L to the power 3, and it's also the reason why we have time complexity L to the power 3. But for the previous method, because you need to multiply two block diagonal matrices, which if you multiply two blocks, it's L cubed, and then you have L blocks, so you have L to the power 4 in this method. But because we have a block, a diagonal block, and then another CTF is diagonal matrix. So one block, the other is diagonal. Then we further reduce by a factor of L. So this is the reason why we also have lower complexity, time complexity. But in terms of space complexity, the L cube is due to the block diagonal. Sorry? Oh, the reason is that so for our So M is at most at N. So M is less than or equal to N. M is a distinct number of filters, so it's less or equal to N. So precisely it should be M times L cube plus N times L cube. But because M is less than or equal to N, I cannot combine the two terms. It's just absorbed into N. But right. So because if I write this down exactly, it should be raised as M times L cube plus N times L cube. It somehow depends on N, but if you consider M, but if you consider the constant, it is upper bounded by N times L cube.
The last space of the lower right block has no N or the space complexity.
Oh, the space complexity. Oh, this is because now the previous method requires to use counter gradient descent method. Because if you look at this solver, you can solve. You can expand this and solve using a linear list system of equations. But this operator has very high dimensions. You can not even do the inverse. So you usually solve this by a conjugate gradient method. But because we can represent everything in a diagonal operator, so we can do a direct inverse. We can do the Hartree division in a closed form solution. So in that reason, we can actually run a batch version without storing all the CTF. We can just run solve for each batch of data, and we don't really increase our space. Any other question? Okay. This shows that this is the real data that correspond to rhythmic activity of your heart and your brain, some protein. And the previous method, as you can show, you can see that the old method takes much longer time than ours, and we have something like 500 times speed up on this real data. But they can really not run on the full size, the full resolution, but we can finish this in 20 minutes on a single CPU, basically, almost. And this is the result from our method, and the previous method cannot run on this data.
This main validation with respect to the summation is a stochastic algorithm or deterministic?
You mean the optimization?
The previous operating problem.
Oh, that
sum over the images. So your comparison is based on stochastic optimization or based on?
if this AI is a diagonal matrix, then it has closed form solution.
Oh no, I mean the summation over I. This I is indexing the images, right?
Right, exactly.
So this is a huge number. So practically, are you using stochastic optimization?
Yeah, you kind of we raise batch of images, batch by batch, and it's like you have system equations. You add the for each batch of image, you compute some quantity and then add them up, one batch by one batch.
Okay.
Oh, okay, so I probably will go quickly and skip some part of this but I want to convey a key message that there's another challenge called contrast variation among the pro-EM images that were not being able to estimate it before, because now we have this constant CI. If you really want to estimate covariance of XI, if you don't consider this variation of CI, it can cause very severe problem, and you can affect the accuracy in the downstream task by large. So none of the previous methods are able to handle these contrast variations. But now if we make additional assumptions, for example, the CI and XI are independent of each other, and you assume that the sum of pixel values in each image is a constant. By these assumptions, you can actually estimate the CI quite accurately. I want to mention that the last assumption is quite reasonable because the sum of pixel value is by the line projection, it is actually the sum of the voxel values of the molecule, which is constant. Okay, now we have actually solved the computation bottleneck, but we want to really focus on contrast variations. So we want to take a detour a little bit, say, okay, how to correct CTF and the denoising. And the previous method say, okay, the nature question is that, okay, if we want to recover CI-XI, okay, what's the best linear estimator in the least square sense? Actually, it has a closed form solution. If you just solve the minimize the expectation, posterior expectation under the assumption of Gaussian noise, you should get this closed form solution. But then, what is the best linear estimator of the contrast? It turns out that we can show that the best linear estimator is that you first do covariance window filtering to denoise the image, and then sum up the pixel values. It should give you the best contrast estimation in the least square sense up to a scale, global scale. And we can further use this useful statistical identity relating the scalar variable and the vector variable, random variable. And so that we have concern about a covariance matrix of Cx and covariance of X without contrast variation, and relate them with variance of this C random variable. And we can further observe that if you multiply all1 vector with this sigma X, the covariance matrix of a clean image without contrast variation, it should give you 0. Because if you combine this 1 and xi minus mu, because xi transpose 1 is a constant. So these two cancel each other and you get 0. Okay, given these two assumptions, you can actually use these two constraints to estimate the contrast variation by the least squares. Okay, assume that you already estimated this sigma of Cx by the original CWF method. Okay. Okay, so based on two constraints, you can actually refine your covariance. And the one last piece is that in the Fourier Bessel space, it only preserves the L2 norm. But all we talk about is okay, the sum of pixel values, but it no longer preserves the sum of pixel values. How can we handle it? There's obviously a gap. But what we can show is that okay, we can use this relation and just replace the R1 vector in the previous description by the Fourier Bessel transform of R1 image, and everything follows. We show that we have much better result than the previous work, and we are actually comparable to Oracle that knows the ground truth covariance matrix. So these two, the middle two are our method, and the last one is the Oracle. We have much better balance between the background darkness and brightness of the molecules because of better estimated contrast. And we can compute the Fourier correlation between the two images for real data, and we can show that our method gives a lot better contrast correction, which was a problem for many previous methods. Okay, so this is a summary of the part 2, and I think we basically solved two problems: the computation challenge and the contrast variations, and there are some future directions. I won't go into details, but you can see there are some common and unique challenges in the two problems, but in very different ways. But both of these two mathematical problems, the group synchronization and covariance estimation, has much broader applications beyond SFM and cryo-EM. So they'll potentially be applied to other regimes. Thank you.
Okay, thanks for the very nice talk. So are there any questions from the audience, or on Zoom? You can type a question into the chat box or the Q&A box.
With the covariance estimation, can you incorporate some other type of denoising? So when you set up the least squares problems, you get a very biased estimator and high noise levels. Even if you debias it, if you subtract it off sigma squared, E is comparable to N, then that might not do a great job. I know in the original CWF paper, they do a kind of eigenvalue shrinkage.
Yeah, we also do eigenvalue shrinkage. We use the same method, but of course, our solver, because we have a closed form solution, it may give much better flexibility to incorporate other constraints or other methods. For example, we can first compute the right-hand side of the linear system equations, and then because it's like a Hadamard division. The solution is like Hadamard division between the two matrices, and then somehow it can be it's like really like a matrix denoising method. It's not like previous method that you have to run a conjugate design method, but now you can regard this as the matrix denoising problem that may be more related to your work. And of course, you can also incorporate other factors like contrast. So for example, if you can estimate contrast beforehand, you know that some images may have higher quality, then you can put more weights for those high contrast images. It can also bring some benefits.
Talk about that.
Yeah.
Any other questions?
I guess it's not covered. Still have
3 and 5.
no,
Oh yeah, that's reference. Yeah. Oh yeah. 3 is is going to submit soon. I mean this week, but I already presented this material in different conferences, but it's still and it's finalizing.
So it is going to be clear.
Yeah.
And just to kind of get an idea, so what, you follow up, you improve the work of Ben Zhang, what impact did the work of Ben Zhang have?
So we had they actually their method was compared and testing many different works, and including some deep learning based methods, and they sometimes use CWF as a benchmark to compare, but sometimes in their method, because many of the data set has many distinct filters, and CWF is not scalable there. So what they did is that they select a very small number of images and then run CWF on it, and then it will give pretty bad result. So it's kind of not a good advertise for CWF, but I think now, because we're using a more efficient method, so it's no longer a problem. But previously, indeed, the CWF assumption on the memory makes prevent many people from using it. But it is still a very common benchmark. Yeah.
I mean, I think in terms of performance, ignoring the memory costs, I think it's sort of the state of the art.
Yeah, it's sort of state of art, and yeah, it's pretty good. The main impact of it is because it's unsupervised and it's ab initio. So not like many methods, like they need to train a model using a clean and noisy pair of images. But now, CWF does a pretty good job, even without any this information. But yeah, it has pretty strong impact.
And so I think the main contribution was more speeding it up, or the visual cleaning.
The contrast variation. So there are two aspects. Yeah. There are two works, one on the accuracy, one on the speed. Yeah.
But the speed up is based on this analytic observation. That we can diagonalize.
Yeah, we can diagonalize. The assumption is that the CTF is radially symmetric filter, so that you can use a special treatment to that filter, but it's not considered in the previous CWF.
That property, that's unique to Fourier vessel, or that one would also be true in the next.
I think it's also true in other steel bases, as long as it gives orthogonal, it's orthogonal transform.
Would it work with prolates?
I think so. Yeah. So we recently have a new implementation of free vessel expansion, where I was one of the contributor of the code, and we were able to further speed up the free vessel expansion by the barycentric interpolation and use some integral identities. But yeah, it's another story. And that actually enables our expansion as a diagonal operator.
That identity is not known previously. Like
I think that's known, but just people somehow didn't use it. Yeah.
Okay, any other questions? Okay, so we'll thank you again.